In drawing electron configurations, it's easier to learn by example. So here we have nitrogen located here in the periodic table. Now, if you remember the orbital diagrams, we have 7 electrons for nitrogen. So we fill the orbitals from lowest energy first, and we proceed to have a spin up and a spin down, and we continue until we have filled the 7 electrons in the orbitals. We fill unoccupied orbitals first of the net general energy. So here we have the 7 orbitals. So when drawing the electron configuration, we have 2 electrons in the 1s orbital. So we would write 1s2. We have 2 electrons in the 2s orbital. So we would write 2s2. And we have 3 electrons in the 2p orbital. So we would write 2p3. And this would be the electron configuration of nitrogen. Let's look at how we can use the periodic table to help us guide us with the electron configuration instead of trying to memorize the orbital diagram. We have the arrangement of the periodic table is that the first 2 groups of the periodic table is the s orbitals. We have section here, p orbitals. Notice that helium counts as the 1s. And then you have your transitional metals in the d orbital, and your f orbitals are your inner transitional metals. So how does this relate to the electron configuration? We know that nitrogen is located here. So we need to go through each element of the periodic table in order of increasing atomic number in order to get to nitrogen. So currently we have 1, 2 electrons in the 1s orbital, and we have 2 in the 2s orbital, and we have 1, 2, 3 in the 2p orbital, which is what we saw when we drew the electron orbital diagram. Now let's try germanium. Germanium atomic number is 32. So when it is neutral, it has 32 electrons. So we're going to put 2, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 20. Now notice how the 3d orbitals are lower in energy than the 4p orbitals. So we are going to fill those next. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and we have 32. So fill degenerate orbitals with unoccupied orbitals first. So here we have the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. How do we use our periodic table to help us to get our electron configuration? So germanium is located right here. The 1s2 corresponds to hydrogen and helium. 2s2 corresponds to these two. In 2p6, we have 1, 2, 3, 4, 5, 6 in the 2p orbital. The 3s2 corresponds to these two. 3p6, 4s2, 3d10, 10 and 1, 2 in the 4p. Now, as you can imagine, that's a lot of orbitals to go through. So we use what's called a noble gas configuration as a shortcut. So again, germanium is located here. Notice that helium corresponds to the electron configuration of 1s2. The electron configuration of 1s2, 2p6 corresponds to neon. The electron configuration of 1s2, 2p2, 2p6, 3s2, 3p6 corresponds to argon. But argon in brackets to signify that this electron configuration is included. And what's left over corresponds to germanium. Now we cannot put krypton because then that would mean argon with 4s2, 3d10, 4p6. And we know that we have 2. Your electron configuration would look something like this. What about plutonium? Plutonium is located here. So if you want to pause the video and try it out yourself, go for it. So the Rn, because it's the previous noble gas, and you have 2 electrons in the 7s2 orbital, and you have 1, 2, 3, 4, 5, 6 electrons in the 5f orbital. Notice that although the 3d orbital is in the 4th row of the periodic table, it is a 3 and not a 4. Same applies for the f, where although the 5f orbital is in the 7th row, it's a 5, not a 7. 4d orbitals, n is equal to the row minus 1. And for f orbitals, the n value is the row minus 2. And so that's why it's 5f instead of 7f. Now there are some exceptions to how electron configurations should be written. The electron configuration that we would expect for chromium would include the 18 electrons from argon, and because chromium has 24 electrons, and 24 minus 18 would leave us with 6 electrons left. So we would fill 1, 2 electrons per orbital, so that would give us 4s2, and the remaining 4 electrons would fill empty orbitals first and give us an electron configuration of 4s2, 3d4. However, there's this empty orbital. Notice how the energy of the 4s orbital is very close to that of the 3d orbital. So the electrons are allowed to transfer between energy levels. And because there's 6 electrons left, the electrons will half-fill the 3d and the 4s. So the electron configuration for chromium would be argon 4s1, 3d5. Try copper on your own. Copper has 29 electrons, and argon has 18. So you're left with 11 electrons to fill. By putting in the 11 electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we potentially have a half-filled orbital here. And it so happens that the electrons are more stable if the d orbital is full instead of half filled. So as a result, the electrons are filled such that the 4s is half filled and the others are completely filled with electrons, which gives copper an electron configuration of argon 4s1, 3,